Great. Thank you so much to Casey for chairing the session and to the organizers for not only inviting me to speak, but just producing a really interesting conference so far. I've gotten really confused, and I've also learned a lot over the last week, which I think is a sign of a great conference and a lot of really good discussions. So thank you to everybody here for that. Yeah, I'm Amanda. I'm a postdoctoral fellow at CITA, and I'm really excited to be talking to you about the two-dimensional binary black hole mass distribution. And oh yeah, this was supposed to be playing the whole time. So I really like this animation. It was made by Zohair Doctor. And this is just a handful of the binary black hole detections that the LIGO Virgo Kagra collaboration has made so far. And I really like this animation because, one, it's super cute and engaging, and you can just like stare at it forever. But also, it reminds us that there are two black holes in each binary, as we all know. But we can get a lot of information from comparing those two black holes together, and they're both equally important to our astrophysical understanding. So that's what I hope to convince you of today. On the next slide. Okay. Okay, so first is our beloved primary mass distribution. I'm showing the full spectrum of compact binaries here. This is a plot I produced for the latest LIGO Virgo Kagra population results. And so this also includes neutron star containing systems. I'm not going to talk too much about those today, but you're welcome to ask me about them because I do spend some time thinking about those. But what I want to point out is a few features in this distribution. So first of all, there's this lower mass gap that is supposed to be there. Maybe if it was originally theorized because of a lack of X-ray binary detections in that mass range. But in the gravitational wave data, it doesn't seem to be completely empty. The first hints of this, I think, were in like 2002, and definitely with more observations, it's clear that this gap is not completely empty in the gravitational wave data, and it's been confirmed with additional detections that are in this region. Instead, what's probably going on is we have two overdensities nearby, and between two local maxima, there has to be a local minima. So the next feature I want to point out is this 10 solar mass peak, where about 90% of the merging binary black holes live. This could be a few things. One of my favorite explanations for it is the stable mass transfer hypothesis that Lika talked about earlier in this conference. Lika's so happy that she's my favorite. And so we're in that scenario, if you require mass transfer to be stable, if you have a lot of stable mass transferring binaries, you get fewer events at lower masses, causing this kind of pileup. Another explanation could just be that it's a feature of the supernova mechanism that's causing a pileup here. But I welcome other interpretations as well. It's not too late to be my favorite. So the next feature I want to point out is this feature at around 30 solar masses. So this was first identified maybe in 2018, and since the LVK has been analyzing this feature, the jury has been out on whether it's a peak, so like a local maximum, or just a shelf. With GWTC4, it's about 80-20 in favor of a peak, but it's still possible that it could be a shelf. This particular model favors like shelf-ish morphology, but the kind of thing that everybody agrees on is that the rate is higher at around 30 solar masses than it is at around 50, 55 solar masses. And I'm going to talk a lot more about this feature later. And I think other people have already talked about it. Okay, this clicker. Okay, cool. Okay, so this is, like, what I wanted to highlight here is that there's been like decades of work on this, understanding this mass distribution. And I think we've made a lot of progress theoretically and observationally. But this is just the primaries, and there's, again, two objects in every binary. And so we can learn a lot, and we're leaving information on the table routinely when we just look at the one-dimensional distribution. And I know it sounds like I'm being pedantic, but this happens all the time, where we just look at the primary mass distribution, and the kind of information that we're leaving out is about binary black hole formation. So even without perfect predictions for exactly what the secondary mass distribution should look like and exactly what the primary mass distribution should look like from your favorite evolutionary theory, we can still learn some astrophysics just by comparing the distributions of primary and secondary masses in the data. So to kind of show an intuitive example of that, I'm going to go through kind of a cartoonish picture of where you might expect differing and similar primary and secondary mass distributions. So the first one is inspired by isolated binary evolution, where two stars are born together in the galactic field. They spend their whole lives together. They transfer mass between each other. There's binary interactions. And then the more massive star dies first, and matter is transferred onto it from the less massive star. So there have been a lot of talks about this. People in this room are much more expert on this than me, but the thing I want to emphasize here is that the first star to die, which is the initially more massive star, is the accretor in this scenario, and the second star is the donor. So that's a different physical process being experienced by the two objects. So after the less massive star dies, M1 and M2 have now experienced different physics because one was the donor and one was the accretor. If this is true on average in the whole population, you would expect different primary and secondary mass distributions. The second cartoon is inspired by kind of dynamical assembly, where you have, I'm just going to stay next to my laptop, two stars forming in a dense environment. A binary forms either because it's a primordial binary or because they found each other in this dense environment, and then you get binary black holes. The ones that eventually merge have undergone different three-body encounters. And as we saw in the really nice videos yesterday, Carl showed one, Johan showed one, these three-body encounters result in something being ejected from the system, and that's how the binary orbit hardens. So the technical term for this is that things get all mixed up in clusters. And on average, the primary and secondary mass distributions are experiencing similar physics. We kind of lose the memory of what was the initially more massive star and what binary interactions happened. And that would lead to different primary and secondary mass distributions. So the upshot is that if there are some processes that break symmetry between the initially more massive and less massive star, you might expect different primary and secondary mass distributions, whereas if something averages all of those out, you might expect similar primary and secondary mass distributions. So the similarity and difference between populations of primary and secondary masses could inform how emergent compact objects form. So I've kind of assigned these labels to these different scenarios because I wanted something concrete. And these are things that we're all familiar with here. But what we're actually sensitive to is not necessarily the details of exactly which evolutionary processes happened, but whether or not M1 and M2 are physically or statistically meaningful labels. So has the more massive black hole undergone, on average, a different physical process than the less massive black hole? That's what we're actually probing here. Although that sounded a little bit too abstract to put into this cartoon. Okay, so what might this look like in the distribution of primary and secondary masses that we measure from gravitational waves? So here's a toy example where the primary mass distribution just has one peak. If the distributions were different, I'm representing that by the secondary mass distribution being flat. This also seems really simplistic, and this one really is, but we do often model the secondary mass distribution as being flat. So I agree that it's simplistic, but it's not uncommon. Whereas if the M2 and M1 distributions are similar, these are identical. Okay, but what we're actually sensitive to in a gravitational wave population analysis is kind of the multi-dimensional population. So of masses, spins, redshifts, inclinations, sky locations, distances. And we're not necessarily only probing one dimension at a time. So a more accurate representation of what we're sensitive to might be this two-dimensional M1, M2 plane. So on the x-axis here, I'm showing the primary mass. On the y-axis is the secondary mass. There's nothing above the diagonal because we're defining primary mass to be bigger. And darker is higher density. So here if M1 and M2 have different distributions, and there's only this peak in M1, we're seeing this vertical band, so only a feature in M1, whereas if they're similar, it's a symmetric picture, so you have a vertical and a horizontal peak. So these look super different from each other qualitatively, so these should be really easy to see which one we're getting in the gravitational wave data. But, yeah.
Is the joint the product of the marginals here?
The marginals is, so okay, that's a really good question. I'm going to talk about this in a few slides. So, so in this case, the marginals are just the joint integrated over, so like the M2 distribution would just be like you integrated out M1. So it's not necessarily a product. But what I'm actually going to be modeling this as is like there's like an underlying primary and secondary mass distribution that I'm combining with a pairing function. So I'll get to that in like 2 slides, and there will be a better picture to show it, if that's okay. Yeah, so what was I saying? Oh yeah, so these look really different, but most theories for merging binary black holes predict that within a given binary, the masses prefer to be equal. So you want to have more symmetric mass ratios. And so as I move to the right on this plot, I'm increasing that preference for equal masses within a binary. So on the far right over here, I have a really strong preference for equal masses, and all of this is moving the density towards the diagonal. And over here, it's really hard to distinguish between these 2 scenarios. So this is an important caveat to keep in mind. Okay, so that was all cartoons and toy models. Now let's look at what we actually get in the gravitational wave data. This is work I did with Maya and Daniel, and we fit the 2-dimensional mass distribution in GWTC3. That's when we, at the time when we did this, that's all we had. And this is what we got. So clearly there's features here. There's features in the M2 distribution. You see these horizontal bands. And there might be features in the vertical direction. There might be features in M1, but it's pretty hard to tell because of these 2 features in M2 kind of obscuring things, and also because there's this preference for equal masses in the binary. So I'd really like to know if whatever bumps in M1 are whether or not they're the exact same feature as we're seeing in M2. So it would be nice if we had those like simple 1-dimensional distributions. So what Maya, Daniel, and I did is we modeled this in a way that we could fit for the preference for equal masses in a binary and then factor it out. So that's what this is. This is how we're doing it. That's what you asked about. So we're fitting for the preference for equal masses with this thing called the pairing function, and what I'm showing here is the underlying primary and secondary mass distribution after we get that. So in green is the primary mass distribution, and purple is the secondary mass distribution. And within the substantial error bars introduced by the data in GWTC3, these 2 are consistent with each other. However, it's definitely possible that they could be different. And in particular, it's possible that there's a bump in the secondary mass distribution that doesn't exist in the primary mass distribution. And this was surprising to me when I first saw it. I kind of thought there was a problem with my model, and we tried to get rid of this, but we couldn't. And this was surprising because since 2018, this had been identified in the primary mass distribution, and nobody was looking at the secondary mass distribution. And now it seems like maybe it doesn't even exist in the primary. So it was a good lesson in checking your model assumptions. So that was GWTC3. The error bars were really large. For the sake of this talk, I updated it with GWTC4. And actually, the support for a higher peak in the secondary mass distribution increased. So you can kind of see that here. So lambda M1 here is the height of the peak in the primary mass distribution. Lambda M2 is the height of the peak in the secondary mass distribution. You can see that lambda M1 is consistent with 0, so meaning no peak, whereas lambda M2 is not consistent with 0. And most of the posterior support is above this lambda M1 equals lambda M2 line. So we're preferring the peak to be higher in the secondary mass distribution, although it's definitely not ruled out that the peaks are the same exact height. So this dashed line goes through the posterior. But if we take this at face value, I think that's a bit puzzling, or at least important to consider when trying to explain what this 35 solar mass peak is. So I'm not sure if this worsens or improves the mid-30s crisis. But with all of the new data in GWTC4, we also have better models. We can fit more complicated and sophisticated models than whatever's going on here. So I think oh yeah, right. I want to know, yes, what process could wash out a feature in M1 or only create it in M2? And I think these models maybe answer that question. So this is a paper led by Hui Tong, who's a graduate student at Monash. And what he finds is consistent with what we were seeing in the previous slides. So I think it's suggesting a real feature in the data. So the upper plot here is a secondary mass distribution. The lower plot is a primary mass distribution. The colors are just different models, but they tell the same story, so you can look at whatever color you want. And these two distributions are clearly different. The secondary and primary mass distributions don't look the same, even by eye. And there's, in particular, this drop-off in the merger rate that exists in the secondary mass distribution between 40 and 50 solar masses, and in the primary mass distribution, it's extending out to over 100 solar masses. I should say that Anaria Ray and Vicky looked at this with a different, more flexible model, and they found that there's potentially just a dip in the secondary mass distribution rather than a complete cutoff. But they still find different primary and secondary mass distributions. So as Aditya explained on Monday, there should be an upper limit to the black hole mass formed from stellar collapse because of pair instability supernovae. However, until recently, I think we were a bit puzzled that we weren't finding evidence for that in the data. I think we were maybe overinterpreting the data a little bit to try to find it or explain why it wasn't there. But I think that was just because we were only looking at the primary mass distribution. Now we're seeing it in the secondary mass distribution. I think that's one good interpretation of what's going on here. So what is the different physics that's making the secondary and primary mass distribution different? What is the primary mass undergoing? So what Hui does in his paper is suggest that this could be caused by hierarchical mergers, where the primary mass is usually a 2G component, so it's formed from previous mergers, whereas the secondary mass is almost always the 1G component. And that's different physics between the secondary and primary mass distribution. And that's consistent with Antonini et al. Has written 2 papers about this that looks at the mass-dependent spin distribution. So far there's hints that that could be what's going on here. So how do we make sense of this in light of the few exceptional events that have been highlighted by the LDK? So we've talked a lot today about GW 231123. There was nice presentations on that earlier. So this is a super high mass event, but the spins are too high to be explained by a typical hierarchical merger scenario. This could be star black hole mergers, so accretion, that's what Fulia talked about earlier. This could be chemically homogeneous evolution. Sylvia talked about that earlier. I've also seen this paper that I think Mathieu is on by Gottlieb et al. Talking about creating this through direct horizon collapse. And there's been many other explanations for this, but none of the convincing ones really invoke the classical hierarchical formation scenario. Even this one requires like isolated binary evolution plus hierarchical. On the other hand, we now have these 2 new gravitational wave detections that are much cleaner detections because they're lower mass, and they have properties very consistent with hierarchical mergers. The spins are like bang on at 0.7. The mass ratios are near a half, but they're 20 solar mass plus 10 solar mass mergers. They're not in the pair instability gap. So these are just 3, though, out of over 100 gravitational wave detections made so far. So we want to look for evidence of this in the population. And inspired by Tom, I thought that if we were just looking at the individual events and trying to explain everything that way, we'd be more like hedgehogs. And I know we want to be more like foxes. So hopefully this is going in that direction. Motivated by this potential evidence for hierarchical mergers and the low mass potential hierarchical mergers, Aditya and I were inspired to look for these in the rest of the population. And again, we can look for them by considering the 2D distribution of masses. So this is a paper, or this is a plot from a paper by Claire Ye, where she's simulating globular clusters with the cluster Monte Carlo code. And the first generation mergers are shown in blue here, and the second generation mergers are shown in orange. You can see that these occur across the mass spectrum, and that they are kind of away from the M1 equals M2 diagonal. So they don't prefer to be equal masses, whereas the the first generation mergers do prefer to be near the diagonal. And this is kind of well established that 2G plus 1G mergers have more asymmetric mass ratios than 1G plus 1G systems. And so these are some of the papers in which I learned that for the first time over and over again. There was a lot of discussion about this plot yesterday. Even in this very massive cluster that Aidan simulated, there's still a preference for unequal mass mergers for the 1G plus 2G components. But if you're worried that's just a trick of the eye, here's a plot we made from CMC outputs, plotting the 1G plus 2G mergers, the mass ratios of them in green, and then the mass ratio of the 1G plus 1G mergers in purple. And you can see that the 1G plus 1G mergers are peaking at mass ratios of 1, whereas the 1G plus 2G are peaking at mass ratios of about 1/2. So we want to look for this signature in the gravitational wave data. It's like super obvious, should be robust. And to do that, we are going to exploit another super robust prediction of hierarchical mergers that just comes from general relativity, and that 2G black hole, which is that 2G black holes should have spin magnitudes near 0.7. This is like more robust than anything that comes out of any simulation. This is just from GR and like angular momentum. So that makes it a really good anchor. So what we're doing with this is we're allowing for the presence of a subpopulation of systems with the primary spin peaking at 0.7. And then, so we're not enforcing that this has to be there, but we're allowing it to be there. And we find that it is there at around 10 to 20% of the time, or it's 10 to 20% of the population. And that's what I'm showing here in green. The rest of the population is shown here in purple. And everything else in this analysis is allowed to vary. And the subpopulation is allowed to have different properties from the main population. So this is, super preliminary work. These are results that I got this week, so please take them with many grains of salt. So when we plot the two-dimensional mass distributions of these two subpopulations, so the highly spinning one and the rest, this is what we get. So in green is that spinning subpopulation. And you can see two things. One, that the primary masses tend to be higher mass, which is what you might expect from hierarchical mergers. And also that there is a little bit more support away from the diagonal here in the green contours. You can compare that to these cluster Monte Carlo simulations and see that, okay, maybe things match up. You can kind of squint at the data and see that, like, okay, maybe there's some orange dots lined up with the green contours. But you might be thinking, okay, we've spent millions of dollars building the most precise ruler on Earth. And it took decades of work by like geniuses that got the Nobel Prize, and you're asking me to use that data and squint. So we can do a little bit better than that. We can do a slightly more sophisticated analysis. So this is another slightly different model. And here I'm plotting the maximum mass ratio of the chi is 0.7 subpopulation, so the spinning subpopulation. And this maximum mass ratio peaks at around 0.6. If I go draw that same 0.6 line on our predicted distribution of mass ratios, that's right between the transition between where you can see a hierarchical subpopulation, and a main population. Thanks. Okay. Cool. So these are the hints we have right now. Again, this is super preliminary, but I just wanted to spark discussion because we have, this is KITP. That's what we're supposed to do. So going back a bit, when I first, at the beginning of this talk and kind of when I first started thinking about the two-dimensional distribution, this is the picture I had in my head, that if M1 and M2 have similar distributions, that must mean that things are getting all mixed up and like averaged out, and that must be dynamical exchanges. And I also thought that binary interactions were the only thing that could cause differing M1 and M2 distributions on average. But this, I would say, is where we are now. I didn't get to talk about mass ratio reversal at all, but I think there's been a lot of really good theoretical work on mass ratio reversal showing that it's kind of prevalent in a lot of systems, and that can kind of average out the binary interactions that would have caused differing primary and secondary mass distributions, so that might be what's happening here. I think, I had heard of mass ratio reversal before, but I was like, oh, that's a small effect, but okay, maybe it's not a small effect. And also hierarchical mergers cause different physical processes between primary and secondary masses. And I also thought that was a small effect, but apparently it's noticeable enough to maybe be showing up in the gravitational wave data now. So it's really nice that this picture has gotten a little bit more complex and we've changed our mental picture a little bit. I'm just speculating here, so I would love for all the theorists to tell me that I'm wrong. Okay, so in summary, there is a physically meaningful difference between the distributions of primary and secondary black hole masses, and maybe a statistically meaningful difference as well. There is emerging evidence for a pair instability gap in the distribution of secondary but not primary black hole masses. And there's potential hints of hierarchical mergers in the binary black hole population. So, okay, I'm done. With that, I'll take any questions.
Questions? Okay, I'll go like that.
Hi, Amanda. Really cool. Lieke Vatson, Radboud University. Super cool work. Really love that you showed all this preliminary work. And I do want to ask about that. Great. So you showed like your Chi 1.7 population.
Yeah.
What do you assume and or infer for Chi 2? Because
yeah. Good question. Let me see if I have that in my backup slide.
And kind of to give a little bit of backup, but I don't know if you know the paper by Asad Hussain, who was finding this like 0.7 population.
Yeah, I do know what you're talking about.
Yeah.
I don't see that,
okay,
though. But it's very few events, or like this is like 10 to 20% of the population.
Mm-hmm.
So it is pretty hard to find like robust things in it. Sorry, this is on a log scale now, so things look different. So this is the Chi2 distribution that we infer, and it's looking pretty flat, but it's not that far from the prior as well. Yeah.
Are they independent?
They are independent in the subpopulation, but in the main population, I'm enforcing them to be the same. Yeah. Okay. Go back to.
Fulya Karola, Northwestern. Very interesting talk. You showed the primary spin peak 0.7, and you also showed they are mostly unequal mass ratios, if I understood correctly.
Yeah.
What are the typical masses of these black holes?
Yeah, this is something these are the details I'm still ironing out a little bit. So I'll show this, but like, please don't take pictures or really believe it that much. So this is the primary mass distribution of that subpopulation in green here. The dashed lines are the priors. So it is, interestingly, like kind of shifted perfectly to the right of the main population by a factor of 2, which is kind of cool. But yeah, it peaks at 20. It's not peaking above the pair instability gap, which I thought was pretty interesting.
Thanks.
Somebody who's next? Okay.
Thanks. So I'm very puzzled by how you or any of the other authors can actually infer any mass distributions. Because when I look at individual events, and you show some of the procedures in individual events, they're extremely broad, and there is absolutely no chance to infer a mass distribution separately for M1 and M2 in any meaningful way. It seems to me that the only way to do anything is to make other assumptions, and rather strong assumptions. Like, for example, some of the authors, I think including you and including Hua, have assumed that there is a universal mass ratio distribution that applies to all events and carries over from low mass events to very high mass events. But the high mass events are the ones where you really cannot measure individual masses. Why should we believe that the mass ratio distribution is the same and is this universal pairing function, for instance? So I'm just curious, like, should I, like, honestly, how much should I trust these? Sorry, not yours specifically, but in general, like, how much should I trust the mass ratio the individual mass distributions? Because frankly, I don't. Are you talking? To be clear, you're talking about this result, or all of the results I showed today? Okay. Sorry, was that a direct reply? Okay. I just wanted to make sure there's like discussion if that's what's going on. So, okay, you asked a few questions. I think that, so there are non-parametric constraints of the mass distribution that don't assume the same mass ratio distribution for everything. I think a good example of that, I think Salvo showed this yesterday, but I'll show it again. So this is one non-parametric constraint. This is the Bin-Gaussian process. So this is not assuming the same pairing function or mass ratio distribution across everything. It is making other assumptions, and it is giving you some statistical uncertainty in the place of making model assumptions. So I think you can constrain the mass distribution. The question of, am I assuming the same pairing function for all masses? And that plot I was showing previously, yes, I am, and that is definitely a problem, and we're working on a mass-dependent pairing function. I could highlight this work by Sharon Benagiri, who's also at Monash, I believe, at least as an odds grav. Where they're finding like a different mass ratio distribution at different parts of the mass space. I'm not going to tell you how much to believe this result, because I still don't know how much to believe this result. But we have enough events that even with the large uncertainties, you can stack them and constrain things in a hierarchical way. Hopefully
On this. I certainly acknowledge Ilya, whatever. I think Ilya has a good reason to worry about this. Mm-hmm. What I will say is that I think it's always good to check with non-parametric analysis. I'll focus most of my talk on non-parametric results and analysis. I think we find that some of the strong features are there, and you'll see our plots. I'll take this as an example. Sharon's analysis is subject to what you worry about. And I'll show it again from our results with an area. When you assume that Q is always a single power law, you can get biased. And this is what's happening here. And I can tell you this is something like this is happening in one of our papers with an area. And it is something to worry about. One has to check and verify. But not all our results are subject to this. The 10 solar mass peak is there, Ilya.
Yeah.
And the mid-30s.
I will also say that in the preliminary work.
The 10 solar mass individual with non-parametric. Wait for my
Yeah, I will also say that in the subpopulation analysis that I was showing, that we are not fitting a single power law as a pairing function to all of the data. We're using a Gaussian, and we're using two Gaussians.
No, what longer. So anyways, it's great results, I think, and one has to look into these things. So yeah, I appreciate what you do very much. I have a simple question, I believe. So for the secondary masses are generally smaller than, well, they are all smaller than the primary masses, right? It looked to me when you compared the mass distribution for secondary and primary masses that the error bars on the curves are rather similar. I would have thought if the primary mass is smaller, the error bar is bigger, than the primary. Sorry, the error bar on the secondary should be larger than on the primary. Is that a wrong idea?
So what we measure for each end spiral is the chirp mass. That's the thing that we measure the best, which is a combination of the masses and the symmetric mass ratio. So we measure the chirp mass really well and the symmetric mass ratio poorly. And then when you deconvolve that into the primary and secondary, you'd get kind of comparable error bars on the two. Yeah, if that makes sense. So the distributions, sometimes you can get a worse error bar in your secondary mass distribution depending on how you model the mass ratio. But in general, the individual events have comparable errors. Other people who are experts on PE should correct me if I'm wrong, though.
Thanks.
Is there a way of like statistically saying whether a non-parametric model is a better fit than a parametric model?
Yeah.
Or vice versa?
Do you want me to leave this to your talk? I'll just briefly say that you can use Bayes factors, and I would argue posterior predictive checks would be better for this. So there's model goodness of fit tests that you can do. But the problem with Bayes factors is that they depend strongly on your prior volume, and non-parametric models have more, like just different prior volumes than parametric models in a way that could be hard to calculate, but there are ways to get around it. I would argue that posterior predictive checks are the best way to measure your model goodness of fit, but they're not as they have uncertainties on them that are pretty large. So it is always a little bit difficult to figure out how good your model is. So what we do in the LVK is we fit non-parametric models and parametric models. We compare Bayes factors within parametric models, and we ultimately are moving towards choosing simple parametric representations of what our non-parametric models are telling us. So we're assuming that the non-parametric result is like going to be the best fit to the data, and then we come up with a parametric model that can accurately capture the features so that everybody else in the community can take power laws and Gaussians and overplot them with their results. Yeah.
Hi, Amanda. Thanks for the great talk. I hadn't seen the marginal of the spin magnitude with the little bump that from the around 0.7. That looks like in the total population, kind of just extending the tail. Yeah.
Yeah.
Some of the, I think GWTC3 analyses that I'd seen that try to do this super flexibly have the envelope plots blow up at 1. Which you're not seeing here. Like, do you think that could be the fact that there is a little bump that you're finding now convolved through their priors could be driving what that's the fact that, or do you think it was just lack of data?
That's a good question. I guess I always assumed that was it returning to the prior. But why would it return to the prior there if we have sensitivity? So yeah, that's a good point. I haven't looked at that. That could be an interesting explanation.
So there was a Ho and Simeon Bird paper in 2024 where we looked at the mixings of the populations. I think we asked the question slightly differently than you did. We were asking whether bump black holes like to pair with other bump black holes.
Yeah,
I was wondering if you could speak to, from your reanalysis and new data, whether these two, is it just the secondary population looks different, or are there distinct populations even amongst the primaries?
Yeah, if I'm remembering this paper right, it's that you're saying things in the 35 solar mass black peak have a very narrow kind of preference for equal masses. Yeah, I think we still find that with GWTC4, and like maybe more clearly than before, and that's like I think now highlighted in the LVK paper. So your question, sorry, was about is that consistent with the primary and secondary masses being similar or different?
Is it a distinct population somehow, these equal mass pairs in that bump?
It could be. I think we have no idea what that bump is, so I think it could be. Yeah, I wish I had a better explanation for you.
Hi, Martina Gruszlińska. I'm not sure exactly how to phrase my question yet, but I was wondering, looking at this feature about 0.7 and the fact that we see hints of evolution with redshift or broadening of the spin distribution with redshift. Is that somehow factored in your analysis, or can it play a role?
Yeah, I really wish I had a solid thing to tell you about redshift. If you've seen me running around looking like haggard and tired, it's because I'm trying to understand our redshift results. So I will say that the broadening of the chi-effective distribution with redshift is either a mass chi-effective correlation, which is what like Fabio Antonini finds in his paper, or spin redshift correlation. It doesn't necessarily have to be both.
I agree, but my question is more like, when I said your result, I was thinking about the fraction of the population that you find in this book.
Yeah, I think, okay, so I'm going to say yes, it could definitely, like it could be that. I'm just not 100% sure yet, so I don't want you to quote me on it, but I do think that's what's happening right now. Yeah.
Thanks.
Because to be clear, like these models, I know people have lots of problems with like strongly parametrized models. We do a lot of tests that don't end up in our papers to check that like we can believe the results. So I'm just still doing those tests. Yeah.
We have time for, one more question.
Do you think this could explain the mass ratio chi-effective correlation?
Yeah, I was talking about this with Aditya earlier. So this is, right, I forget if I highlighted this, but this is work I'm doing with Aditya. This is not just me. So yeah, I think this could explain the chi-effective mass ratio correlation. And specifically, so in the latest LVK results, it's found that the width of the correlation could change, or the mean of the correlation could change. So if it's the width of the correlation that changes, this could definitely be that. This would cause the same exact thing. Yeah, we have a plot somewhere in a Slack channel showing that. Yeah, so that would be a really nice consistent picture if this was all explained by hierarchical mergers, but I don't want to overclaim. Yeah.
Okay, maybe Shemek, you want to go up and start saying we could do one more question while we switch. We have one last.
This is the pointer.
Well, okay. So this might be very hard to answer now that Amanda has taken her slides down.
Oh, sorry.
The change in the phenomenology of the shape of the lower mass gap compared to like 03 versus 04.
Yeah. Right.
Have you guys looked at how prior volume terms affect the inference?
That's a good question. So what Rita's referring to is this, like, the lower mass gap could either be a gap or it could be two local maxima. And now that we're modeling it as two local maxima, the gap has changed shape. Could that be a prior volume thing? It actually could, because, the notch filter thing that we were using before takes up more prior volume than a Gaussian. A Gaussian doesn't take up that much prior volume, which is now how we're modeling it. So yeah, it could be that, I think, but I haven't looked into it specifically to see if that's exactly what's driving it. Yeah.
Okay, so let's thank Amanda.
Oh, sorry.